Try again. All right, so first thing we're going to do is work some problems dealing with dissolved oxygen and primary productivity. When you hear the word productivity, what should you think? Like producers, what is that about? Producers, what is that about? Photosynthesis, doing photosynthesis. When we talk about production, we need to think about what our plant's producing during photosynthesis. Glucose and oxygen gas, right? Glucose and oxygen gas. Those are the things that are getting produced by either plants or algae or some bacteria, right? Now, we've got several problems that we're going to try to do. Let's look at this first one. An experiment involving one fish in a tank of water was conducted to try and measure the amount of carbon that the fish consumed over the course of the day. Or it could say fixed over the course, well, consumed is probably good. The fish was placed in a 1-gallon fish tank and then covered with the same pond water in which it was living. The initial amount of dissolved oxygen in the water was determined to be 8.52 milligrams of oxygen per liter. The fish tank was then placed under a light source for 24 hours. The final reading for dissolved oxygen was 12.49 milligrams of oxygen per liter. The fish tank remained at 6 degrees Celsius the whole time. Calculate the total amount of carbon that was fixed based on the change in amount of dissolved oxygen over the 24-hour period. Now, that's not a perfect problem because can a fish fix carbon? You know, the plant fixes the carbon. Can fish do photosynthesis? No. The plants fix the carbon and then the fish what? Ate it. But here's the deal. You've got a section on your formula sheet called, let me find it on there. It's called primary productivity calculation. It's on this side of the sheet. And you've got these two formulas on the sheet. Now what you don't have is that top one. And I think I would write that above it on your sheet. What's the little triangle mean? Change in, what's DO stand for? Dissolved oxygen. And that's equal to final dissolved oxygen reading minus initial dissolved oxygen reading. Now before I work the math on this one, a little bit of background. Do fish breathe the same oxygen that you breathe? Yes. It's just oxygen that's dissolved in the water. How much oxygen is there in the air? Like what percent of the air is oxygen? Close to 16 to 20. It's pretty close. But in water, it's way less than that. It's like 4 or 5%. Way less oxygen in the water. If there was the same amount of oxygen in the water as there is in the air, what could you do? You could jump in and suck in some water, and you could breathe it. No problems. But the issue is there's not as much. Not enough to keep you alive. Another thing I want to mention before we do the math is things that affect how much oxygen is in the water. And this is stuff we talked about before. When you put a pump in your aquarium, what is that doing to the amount of oxygen in the water? It's increasing it because it's doing what to the water? What does the pump do? It moves it. And as it's moving, what's that water doing to the air above it? Moving water, what's it doing to the air above it? Rubbing on it. And what's happening to some of that air? Dissolving into the water. So what's going to have more oxygen, a river or a pond? A river, because it's moving, right? What's another thing that affects the amount of oxygen in a body of water? Temperature. Hotter means more or less oxygen in the water? Less. As the water gets hotter, the gas bubbles out, right? If you put a Coke, which has a lot of CO2 in it, in your car in the summer, as it gets hot, what happens to that CO2? It comes out. If you let the Coke cap in your car, it might explode, right? Because the CO2 comes out. Another thing that affects it is how many plants are in the water. What should plants be doing to dissolve oxygen levels?
Photosynthesizing.
And therefore doing what to dissolve oxygen levels? Raising them, right? Because they give off oxygen. On the other hand, the more bacteria or animals there are in the water, what should happen? It should go down, because what are they doing? Using it to do cell respiration. They're just dropping it. And another thing that matters is salinity, saltiness. Salty water better at dissolving oxygen or worse at dissolving oxygen? It's worse. So knowing those things will help. But let's look at the math on this. We have 2 readings. Let me go to a slide where I can work this out so people who are just listening to this can see. We have 2 readings in this problem. They give us an initial and a final reading. And they tell us to start with the amount of oxygen was 8.52 milligrams of oxygen per liter of water. And then a little while later, we put this tank in front of a light. And later we measured the oxygen there, and the reading was 12.49. Now, when you have a problem like this, the first thing you need to do is calculate how much the dissolved oxygen changed. And like the formula tells you, you take your final dissolved oxygen measurement minus your initial dissolved oxygen measurement. So in this case, it's going to be 12.49 minus 8.52. And when we do the math on that, that gives us a change of 3.97. And remember, the units on that are milligrams of oxygen per liter of water. Why did the dissolved oxygen go up? What's going on with the tank in this problem? What did it say the tank is? What are we doing to the tank in the problem? It's in front of a bright light.
Evaporating.
What's happening in the tank? There are plants in the tank. What is happening in the tank? Photosynthesis. The photosynthesis is making oxygen, right? Photosynthesis must be happening faster than what? Cell respiration. So that's our change in our dissolved oxygen levels. The next thing you want to do is go back to your formula sheet, and it tells you when you're doing a primary productivity calculation, you can take this formula right here, milligrams of oxygen per liter times 0.698 will give you the milliliters of oxygen per liter of water. So this is just a conversion step. So if we have the amount of oxygen in milligrams per liter, if we multiply it by that, that gives us the milliliters of oxygen per liter. We're just converting. So in this case, we need to go 3.97 times 0.698. Just multiply it out. That gives us 2.77 milliliters of oxygen per liter of water. But the problem wants us to find out is how much carbon got fixed. This is how much oxygen got made, right? But in photosynthesis, as oxygen is getting made, what's getting fixed? Carbon, because it's getting used to make what? The carbon used to make sugar. So in the other formula on your sheet, this one, liters of oxygen per liter of water. I should say milliliters of oxygen per liter of water. If you multiply that by 0.536, that will give you milligrams of carbon per liter of water. So, in this problem, I'm going to make a little space up here.
Steve, please go to the guidance office. Steve Scott, please go to the guidance office.
So in this problem, we know right here the milliliters of oxygen per liter of water. 2.77. If we plug that in right here in the equation, and we multiply it by 0.536, that will give us 1.48 milligrams of carbon per liter of water. And again, that's called a primary productivity calculation. It's letting us figure out, by measuring how much the dissolved oxygen levels change, basically how much sugar got made. Because the carbon that's being fixed is in sugar. It's just one of the plug and chug things. Calculate the change in dissolved oxygen, and then use these two formulas, this one and this one, to convert that oxygen to milligrams of carbon fixed per liter of water. Plug and chug kind of formula. Now the next calculation is kind of a similar thing. Before I do that though, I've got this diagram over here on the board. Dissolved oxygen levels in a pint versus time of day. So let's say this was in the summer. What do we just say temperature does to the amount of oxygen that dissolves in the water? Higher means less, right? But this kind of looks opposite of that, right? When's the hottest part of the day? 3 or 4 o'clock is actually the hottest part of the day. And notice that's when the oxygen levels are at its highest. How could you explain this? Why are dissolved oxygen levels going up in the morning, starting to go down in the late afternoon? How come?
The sun's overhead.
The sun's overhead, and what's happening in the water? Photosynthesis. Photosynthesis is raising those levels, and when the sun goes down, it starts to drop. That being said, when we talk about net and gross productivity, gross is the total amount of what done? Gross productivity would be the total amount of photosynthesis, the total amount of sugar made or oxygen released, right? Net is what's left over after you take out what? Respiration. So you've got an equation right here, an important equation. I don't think this one's on your formula sheet, so it's one you might want to add. What's NPP? Net primary productivity equals the gross primary productivity minus, what's the R? Respiration. So let's look at how we would use that. We've got 3 problems that all deal with this formula. Water with algae inside is placed in a completely dark environment. If it's completely dark, what's the only thing happening in that bottle? Respiration, right? Photosynthesis can't happen in the dark. So only respiration is happening in this bottle. It's in the dark. If the initial dissolved oxygen concentration of the water is 12 milligrams per liter, and the dissolved oxygen after 1 hour in darkness is 8 milligrams per liter, how much oxygen is consumed by the plants per hour? What's the answer? If you start with 12, and after an hour you have 8, how much got used? 4. So the rate of respiration is 4 milligrams per liter per hour, right? 4 milligrams per liter of oxygen are used every hour. That's the rate of respiration. What process consumes this oxygen? Cell respiration. What things on Earth do cell respiration? Every living thing. Plant, bacteria, fungus, animal, everything in between. And 39. A bottle of water with algae inside is placed in a sunny environment. If the initial dissolved oxygen concentration of the water is 12, and the concentration after 1 hour is 25, how much net oxygen is produced per hour? What would that be? We started with 12, we ended up with 25, it would be 13, right? So this will be 13 milligrams of oxygen per liter of water per hour. We'll come back to this, how much carbon is fixed during the same period. Is that the total amount of photosynthesis done? The 13? What's going on at the same time? Respiration, right? So that's net primary productivity, right? So that's taking into account both. Some oxygen is being used, at the same time some is being made. So the last one, assume the bottles described in problems 37 and 38 are the same bottles. What is the gross productivity in milligrams of liter per oxygen? Go back to this formula. Net primary productivity equals gross minus respiration. What two things do we already know from the first two problems? Net. This is respiration, right? And this is net. So we need to find gross. So if we did a little bit of rearranging of our equation, gross primary productivity would be equal to what? Net plus respiration, right? We got to add that R to both sides. So now if we add them up, we get how much gross primary productivity? 17. 17 milligrams of oxygen made per liter of water every hour. Does that make sense? So net primary productivity is equal to the gross minus respiration. How much total photosynthesis is done minus how much oxygen is used by respiration gives you what's called your net primary productivity. We've kind of talked about that before, but never in a lot of detail. Now let's look at one we have done before. This is talking about Gibbs free energy. What's another word we might use to mean basically the same thing as free energy? Activation energy, right? It's energy available to make something happen. An experiment determined that when a protein unfolds to its denatured state from its original folded state, the change in enthalpy, it's like the total amount of energy, delta H, is 53,000 joules per mole. And the change in entropy, delta G, is 175 joules per mole times Kelvin. What's entropy? Disorder, chaos. Which law says that every time there's a reaction, entropy increases? Second law of thermodynamics. Exactly. So we want to calculate the change in free energy that occurs if the protein unfolds at a temperature of 20 degrees Celsius. And then we got some questions to answer about. So let's go to a blank slide here. On your formula sheet, there is a section about Gibbs free energy. And it gives you this formula. Delta G equals delta H minus T times delta S. And remember that delta G is free energy. Delta H is what? Change in enthalpy. Minus T. What kind of T does that have to be? Kelvin. And then the change in entropy. So we got all those things. It's just a plug and chug problem. In the problem, it tells us that the delta H is 53,000, and that's joules per mole. It tells us that the temperature is 20 Celsius. So what do we need to put in for the temperature? So 293 Kelvin, right? Times delta S. And it tells us that delta S, the change in enthalpy, or entropy rather, is 175. Now notice these kelvins cancel out. So now let's do a little math. Let's go 293 times 175. And that's 51,275. And we've got to subtract that from this 53,000. So when we do the subtraction, we get an answer of positive 1725 joules per mole. That's where those questions come in. That's your answer to the first question. But the next question was, is this reaction spontaneous or non-spontaneous? What's the answer? Non-spontaneous. What does that plus in front of the delta G tell you? To make the reaction happen, you have to what? Add that much energy. That's the amount of activation energy needed to make this happen, right? If you get a positive delta G, the reaction's always non-spontaneous. And the other question on that slide was, is it endothermic or ectothermic? Or not ectothermic. Well, endergonic or exergonic. And I said endothermic and ectothermic, I think. Endothermic reactions do what? Endothermic or endergonic? What do they do? They have to have energy added to make them happen. In exergonic or ectothermic reactions, they do what? They give it off. Which one is this? Endergonic or endothermic? That's how much energy you have to add to make that reaction happen. Non-spontaneous. If you get a positive delta G, it's non-spontaneous. That's how much energy you have to add to make it happen. Does that make sense? Let's do one more of those just to make sure you got it. So here's another one. An experiment determined that when a protein, it's the same basic wording, unfolds to its denatured state from its original folded state, the change in enthalpy is 59,000 joules per mole. The change in entropy is 190 joules per mole. And at a temperature of 22 degrees C, calculate the free energy in joules per mole. So, on this next problem, again, remember the equation. Free energy is equal to change in enthalpy minus the Kelvin temperature times the change in entropy. In this problem, it tells us that the delta H is 59,000. It tells us that the temperature is 22 Celsius, so that would be what? 295 Kelvin.
What is this? 298.
Add 273 to your Celsius. And then the delta S is 190. So now we multiply that out. We go 295 times 190. And that comes up to be this. Those kelvins are going to cancel. And we've got to subtract that from 59,000. And again, we get a positive number. And if delta G is a positive number, what does that always tell you? It's a non-spontaneous reaction. That's the amount of energy that you have to add to it to make it happen. And therefore, it's also what kind of reaction? Endergonic. Does that make sense? If you got a negative answer, that means it's what kind of reaction? Spontaneous and exergonic, because a negative delta G means it's giving off heat or energy. All right. Everybody okay with that? Plug it in and work it. Just plug and shove. All right. The next thing is something that we did a long time ago. Let's refresh our memories. The pH scale runs from what to what? 0 to 14. What's pH stand for? That's for power of hydrogen. On the pH scale, where are the acids? 0 to 7. These are the acids, right? And these are the bases. Also remember we've got this other thing called pOH. Whereas pH measures the concentration of H pluses, pOH measures the concentration of, what's OH? Hydroxides. Now they're kind of reverses because together pH plus POH, those have to add up to be what? 14. So if you have a pH of 4, what's your POH? 10. I'm just going to write 10. I'll write the POHs out here in red. But remember, they have to add up to be 14. So if the pH is 4, that's not red. The POH would be 10. And would this be acid or base? Just look at the pH. If the pH is below 7, it's what? It's an acid. So POH would be 10, and it would be an acid. Here we've got a pH of 8, which means we have a POH of 6. And is this an acid or a base? It's a base. Strong or weak base? Pretty weak, because where's the strongest base at? What pH? 14. And where's the strongest acid at? 0. So this is pretty weak. Here we've got a pH of 13. So we have a POH of 1. And this would be really basic, right? pH of 1, POH of 13, and it would be really what? Really acidic. Where's the only place in your body you might ever approach that? In your stomach. POH of 6. This time I'm giving you a POH. What would the pH be? 8. And that would be what? A base. pH is above 7. POH of 9. pH would be 5, and it would be an acid, but not too acidic, right? This would probably be about the acidity level of Coca-Cola or something. A little acidic, but not too much. POH of 2. pH would be 12, and it would be pretty much pretty basic. If you have a POH of 12, you would have a pH of 2, and that would be really, really acidic, right? Is everybody okay with this? Pretty. All right, let's do some water potential problems. Kind of talked about those in class today if you were in an A class. Calculate the total water potential for the following solution. The molar concentration of a sodium chloride solution in an open container is 0.2. The pressure potential of the solution is 0. What is the total water potential at a temperature of 32 degrees Celsius? So, on your formula sheet, you will find an equation for water potential. What's this funny little symbol called? Psi. My board's a little off up at the top, so it's going to look kind of sloppy. And now, what total water potential is made up of two pieces? What's the S stand for? Solute. And the P? Pressure. Now, something to remember before we try to work the problem. Water moves which way in terms of water potential? High to low water potential. And the more solutes something has in it, what happens to the water potential? It goes down. And the more pressure, it obviously goes up. Now, you also have a formula on your formula sheet for calculating the solute potential part of this. So we've got two formulas. Now, the nice thing about this problem that we just read, what does it tell us about the pressure? It tells us the pressure is 0. So we don't really have to worry so much right now about the pressure part of this. We just got to calculate the solute part. Now, it tells us a couple of things we need to know. It tells us, first of all, that it's sodium chloride. A solute, sodium chloride. What kind of compound is sodium chloride? It's a salt, which means it's held together by what kind of bonds? Ionic. If it's got a metal in it, it's ionic.
Is that negative ICRP?
Yes. All right, and what happens when you put a salt in water? It disassociates. It breaks up into ions. Na plus and Cl minus in this case. For every formula unit of this NaCl you start with, you get 2 moles of ions, right? That's what I is asking us for. I is the ionization constant. And the way we figure that out, for every 1 formula of the salt we start with, how many moles of ions do we get? In this case, we get 2. Now, if this had not been salt, if this had been sugar, C6H12O6 or some other sugar, sugars are held together by what kind of bonds? Covalent. Do they break up into ions when you put them in water? Do they break up at all? No. So if it's a sugar, what's I going to be? Just 1. But for this, it's 2. So we got -2. What's C stand for? The concentration, the molarity. And it tells you that on your sheet. And in the problem, it tells us that our concentration is 0.2. So we got -2 times 0.2. And what does that big M stand for? It's a molarity, but what's a molarity mean? Moles of solute per liter of solution, right? Moles per liter. R is a constant. It's going to always be given to you, and it's on your formula sheet. It's called the pressure constant, and it is 0.0831. It's got some weird units on it, but that's given to you too. Liter bars over moles times Kelvin. Which means when we plug in the temperature, we need to plug it in now as a Kelvin temperature. Now this problem told us that the temperature was 32 Celsius, so that's how much Kelvin? 305. So let's cancel out units. The kelvins will cancel. The moles here cancel with the moles here. And the liters right here cancel with the liters right there. So we're just left with what? Bars. That's a pressure unit. That makes sense. And now if we multiply this out, 2 times 0.2 times 0.0831 times 305. So we come up with about -10.1. That's the solute potential. But since pressure was 0, it's also what? The water potential. Does that make sense? Let's try another water potential problem. Here's a similar one. Notice this time we've got glucose, which is a what? Sugar held together by covalent bonds. Other than that, it's the same basic problem. So again, we go back to our formula. Total water potential is equal to solute potential plus pressure potential. And solute potential equals -I CRT. The problem tells us the pressure in this one is 0. So we plug in what we know. Since it's a sugar, what's I always for a sugar? 1. So we got -1 times C. What's C here? 0.3. That's moles per liter. Your pressure constant is 0.0831. And again, that's liter bars over moles times Kelvin. And we have to put the temperature in Kelvin. It's 37 Celsius. So how much Kelvin is that? 310. Yeah, 310. It's not 3. Yeah, 103. All right, Kelvins cancel. The moles cancel. The liters cancel. And if we do the math, 0.3 times 0.0831 times 310, we end up with about -7.73. Now, I want you to think about something. Let's say that we took that solution from the last problem. What was the water potential in the last problem? Let's just say -10. Okay? So let's say here we have a total water potential of -10. And we put that inside like a dialysis bag. And then we put it in a beaker filled with this solution, where the water potential is negative 7.73. What's water going to do here? Assuming neither solute can move, what's water going to do? It's going to go in. Because water always goes from higher to lower, right? Negative 7 is a bigger number than negative 10. So water would move in. And it would continue to move in until one of what two things happen. Either the pressure kept any more from going in, the water potential is equal, or the cell just what? Bursts. And that's probably only going to happen if it's what kind of cell? Animal cell without what? Without a wall. All right, let's try to work one more. Another water potential problem. Notice what we've got. Sides A and B are separated by a semi-permeable membrane. The triangles represent solutes that are dissolved in water. If the volumes of the two sides are initially equal and the membrane is impermeable to the solute, which way will the water flow? You guys tell me. Water always moves from less concentration of solute to more concentration of solute, right? So the water is going to move like that. Low solute concentration to high solute concentration, correct? What is the total water potential on each side of the membrane? Well, we know that total water potential. Let's try that again. We know that the total water potential is equal to the solute plus the pressure. So over here we know that we've got negative 1.7 plus 0. So on this side it's negative 1.7, right? And over here, negative 0.6 plus 0. We said water moves which way in terms of water potential? Higher to lower. That still tells us it's going that way. Which side is hypertonic? Hypertonic means more what? More solid. So this side's hypertonic on the left. This side's hypotonic. And another way of defining osmosis is it's the movement of water from what to what? Hypo to hyper. All three ways we looked at it said the water's going that way, correct? Last question. What will happen to the volume on side A? It's going to go up because water's moving over that way, right? And what's going to happen on side B? It's going to go down. We got a minute or two. Let's do one more of these real quick. I know y'all are in a hurry to get out of here, but let's do one more. Same kind of problem. Same kind of problem. Sides A and B are separated by a semi-permeable membrane. The triangles represent solutes that are dissolved in water. If the volumes of the two sides are initially equal and the membrane is impermeable to the solute, which way will the water flow? No, it's not the same question. It's not the same question. Numbers are different. Okay? Now it still looks like, just in terms of solutes, the water ought to go this way, right? But what do we have this time that we didn't last time? We got some pressure. Something's pushing on this side, right? Maybe there's a wall over here, but there's not one over there or something. There's something pushing on this side. So before we can really answer question one, what do we better do? Find the water potentials. In terms of solutes, it wants to do this. The water does. But maybe it can't because of the pressure. So over here, the total water potential would be what? Positive 0.3, right? Because it's negative 1.7 plus 2. So over here, the water potential is positive 0.3. Over here, it would be what? Negative 0.6. So in terms of water potential, which way is the water going to go? It's going to go from higher water potential to lower water potential. It's actually going to go that way because of the what? The pressure. That's why pressure is important. Pressure's pushing it the other way. Let's see, we just answered 2. Which side's hypertonic? This side's still hypertonic, right? Still got more solutes. This side's still hypotonic. So the water wants to go this way. But it can't because of what? The pressure. the pressure stopping it from going this way. So what will actually happen to the volume of side A? It's actually going to decrease because that water's getting pushed over there. And this on side B, the volume is going to increase. Make sense? Good place to stop. We will continue in the morning. We'll finish.